Welcome folks, today discussing advanced applications of integrals, in particular arc length. So we'll give you some background, we'll do a couple examples, and then we'll finish discussing arc length as a function. So here's the background. Suppose that a bug is walking along the graph of y equals f of x from some point defined by the x value a to some point defined by the x value b. We'd like to know how far it travels. So here's the idea. Here's the curve, and we're thinking of this curve going from A to B. And as usual, the way we'll stylize this is sort of by discretizing or dicing our interval from A to B up into n subintervals of equal width, delta x. So on each subinterval, we'll connect the points associated with that subinterval by a straight line. And it turns out that the length of that straight line will give us an approximation for the length of the curve. So here's what I mean by that. The straight line here has some length that's just given by the Pythagorean theorem. So we see that we can express the hypotenuse of this triangle as it pertains to delta x, which is the change in the x value, and delta y, which is the change in the function value. Accordingly, therefore, we see that this expression for the distance between the ith point and the I minus first point as the square root of the sum of two squares, exactly as the Pythagorean theorem states. I'm going to refer to this length as L sub I, the length of the ith interval. So we'll go ahead and manipulate this as follows. I'll go ahead and look at that length L sub I and manipulate the inside expressing x sub I minus 1 minus x sub I as delta x, and then multiplying and dividing our expression f of x sub I minus f of x sub I minus 1 squared, also by delta x squared. We can see, therefore, that we can factor out a delta x. And after we do that, we see that this quantity here in parentheses is actually equal, by the mean value theorem, to f prime of x sub I star, where x sub I star is between x sub I minus 1 and x sub I. Okay, and this again is due to the mean value theorem. The mean value theorem relates the slope of that secant line to the slope of a tangent line somewhere in between. Now, if we'd like to know the total length, an approximation for the total length, we can add up all of these bits of length, and it turns out that we'll get a Riemann sum here. So here we see that approximation for the total length. I'm calling that L as the sum I equals 1 to n of the quantity 1 plus f of x sub I squared, square rooted delta x. And of course, as n goes to infinity, our x sub i's become x's, our delta x becomes a dx, and our sum becomes an integral, which in this case is on the interval from a to b. So here is our expression for the length of the curve y equals f of x from the point defined by the x value a to the point defined by the x value b. That arc length is the integral from a to b of 1 plus f prime of x squared, all square rooted, dx. And this is sort of the bottom line with our arc length. Okay, let's have a look at a couple examples. Here's the first one. Let's determine the length of the curve y equals the square root of x cubed from the point defined by the x value 1 to the point defined by the x value 4. So we'll go ahead and just use our formula for arc length here and evaluate the associated definite integral. So here again, we see that function written in power function form, x to the 3/2. We can quickly compute the derivative as 3/2 x to the 1/2, and that allows us to write down an expression for this arc length, the integral from 1 to 4 of 1 plus the quantity 3/2 x to the 1/2 squared, all square rooted dx. So again, here we see that integral for the arc length. Simplify the integrand, make a u substitution, u equals 1 plus 9/4 x. Obtain an integral in u world with some new limits, evaluate that integral, and we can see the arc length here, some number 3/2 times the quantity 10 to the 3/2 minus 13/4 to the 3/2. Okay, super. So I won't go through the derivation, but if the curve is defined by x equals g of y from y value of c to y value d, similarly, the arc length is an integral involving this sort of Pythagorean identity, g prime of y squared plus 1 all square rooted. In fact, if we think about our arc length here in terms of infinitesimals, differentials as ds squared, it's dx squared plus dy squared, it makes it sort of quick and easy to derive an arc length formula for either ds in terms of dy dx or ds in terms of dx dy. So this is sort of a quick way to think of arc length as the square root of the sum of a little bit of arc length ds is the square root of the sum of dx squared plus dy squared, and then you can take it either direction you want. So the formula we have here is sort of the one of the flavor dx dy squared plus 1 dy. Now this approach being able to go seamlessly between thinking of arc length as a function of x or as a function of y will be useful also in our next investigation on surface area. So let's go ahead and have a look at an example here. Let's think about the length of the curve x equals y squared from 0, 0 to 2, 2. So we'll go ahead and write down the integral and then evaluate that definite integral. So here this parabola actually has arc length given by the integral from 0 to 2 of the square root of the quantity y squared plus 1. Now here's a sum of squares that we can evaluate with the trigonometric substitution. So here we see our trigonometric substitution. Y is tangent theta. Of course, that gives dy is secant squared theta d theta, and y squared plus 1 is secant squared theta also. That allows us to express the integral as the integral from 0 to alpha of secant cubed theta d theta. And of course, alpha is the value satisfying tangent of alpha equals 2. Now, if you remember anything about an antiderivative of secant cubed, you might remember that it's by parts reproducing the original integral. So I won't go through that in all of its glory here, but I'll go ahead and write down the associated definite integral using the fundamental theorem of calculus. So here we see that antiderivative 1/2 secant theta tangent theta plus the natural log of the absolute value of secant theta plus tangent theta evaluated between 0 and alpha. Now, of course, if we know that tangent of alpha is 2, we can construct an expression for the secant of alpha also. We see that when tangent alpha is 2, of course, the hypotenuse of the corresponding triangle is the square root of 5. That tells us the secant of alpha, the hypotenuse over the adjacent, is square root of 5. And this allows us to write our expression in terms of 2's and square roots of 5. So here's the arc length of that parabola. Seemingly innocuous curve with arc length involving the antiderivative of secant cubed, we end up with 2 square root of 5 plus the natural log of the square root of 5 plus 2, all divided by 2. Okay, super. All right, let's go ahead and talk about arc length as a function. This again will be useful later on. So it's often convenient to express arc length as a function. We'll go ahead and let s of x represent the length of the curve y equals f of t from p to q, where q is defined by some unknown point x. So here we see just some curve f. I've written it as a function of t so that we don't confuse the curve, the variable in the curve with the variable endpoint here, x, but you can imagine wiggling this point x around wherever you want to so that it's a variable. We can certainly write the arc length of this function as a function of x just using our formula. So here we see that arc length as a function of x, the integral from a to x of 1 plus f prime of t squared, all square rooted dt. Now, we'll notice that this is of fundamental theorem of calculus form. And since our arc length function is a fundamental theorem of calculus form, we can go ahead and write the derivative ds dx as the square root of the quantity 1 plus f prime of x squared. That's going to be useful later also. Okay, in the meantime, let's go ahead and just have a look at the arc length function for this curve y equals t squared plus 1/8 natural log of t. And here we'll just take the starting point to be 1, 1. Okay, so in doing so, what we'll do here is go ahead and find the derivative, evaluate the integral, and then use ending point x. Okay, so here we see our function t squared minus 1/8 times the natural log of t. The derivative is quickly computed. And something sort of interesting happens when we go ahead and expand f prime of t squared and add 1. When we do that, we end up with this expression that looks a whole lot like that quantity squared. That tells us it factors, and it factors like 2t plus 1 over et quantity squared. That actually makes our integral a lot easier. So here's our arc length function. The arc length function s of x is the integral from 1 to x of the quantity 2t plus 8 over t all squared, square rooted. So we end up here with t squared plus 1/8 times the natural log of t evaluated from 1 to x. This is a quick fundamental theorem of calculus evaluation, and we can identify the arc length function here as x squared plus 1/8 times the natural log of x minus 1. Okay, folks, so a nice clean functional form for the arc length function. If you wanted to know the value of the arc length ending at 3 or 4 or 10, you could just plug into this function and you get out the arc length with that starting point 1, 1. Okay, folks, hope you've enjoyed this video on arc length. Have a great day, and we'll see you next time. Bye-bye.